With the sheet for section 6.3 in your hand and successfully printed out, or however you have obtained it, if you could go ahead and graph the 2 to the x power. It's fully a review problem. We just did it a few minutes ago, but we are going to use 2 to the x to introduce the concept for today. So I'm going to give you 60 seconds or less to reproduce the graph for 2 to the x power. 2 to the x power, if I plug in the x value 3, the y value is going to be 8. If I plug in 2, the y value is 4. If I plug in 1, the y value is 2. If I plug in 0, the y value is 1. And then if I plug in -1, the y value is 1/2. And so here is my graph of 2 to the x. There shouldn't really be any mystery there. We've graphed that now a couple different times. I didn't ask you to do this because we just did it in the last section, but I'm just going to regurgitate this so that it's on this page. And so then we know that the domain of the 2 to the x graph goes fully left and right from -infinity to infinity. And then the range of this graph goes from 0, which is the boundary, it never equals 0, to infinity. Okay. So the reason I have resurrected that is now what we're going to do is we're going to merge the material from section 6.2, which was on this exponential function, with the material from the previous section, which was about inverses. Woohoo! So we're going to talk about the inverse of the exponential function. So what I would like you to do first is exercise 2, just like we did when we talked about inverses. I would like you to use the points on this graph right here to graph the inverse of the exponential, and then propose what you think the domain and the range of the inverse are. And just for kicks, just in case anybody doesn't remember, how do you make the inverse of a function? What do? You flip the x's and the y's. Yes, that is it. There will be, but not till section 5. There shouldn't be anything like that in section 2 because you don't know how to do it yet. I'm a mean math teacher, but I'm hoping I'm not exactly. All right, so I'm sorry. So I'm going to go ahead now. I'm going to flip the x's and the y's, and we're going to see what the picture of the inverse is, and then we're going to build up from there. So this is the point 3, 8. So when I flip it around, it becomes the point 8, 3. The next one is the point 2, 4. So when I flip it around, it becomes 4, 2. Next, we have the point 1, 2. It becomes 2, 1. This point on the y-axis is 0, 1, so it becomes 1, 0. And last but not least, I've got the point -1 and then a half, so it's going to be a half and then -1. So those are the points. Now, I'm hoping, as you were considering the domain and the range, and we'll connect the dots in a minute, but I'm hoping as you consider the domain and the range, you remember something we talked about, that since we flip-flop the x's and the y's, the domain and the range of the inverse are just related to the domain and the range of the original function. What's the domain of the inverse going to be? Yeah, it's just going to be the range. The x values of the inverse are the y values of the original function, so 0 to infinity. The reason that's important is notice what this tells me is that my inverse is never going to be equal to 0. It's never going to hit the y-axis. What's the range of the inverse going to be? Exactly, it's going to be the same as the domain of the original function. The x values of the original function become the y values of the inverse. So -infinity to infinity. So my graph should match that data. And so this is what my graph looks like. This is the picture of the inverse of the exponential. And we're going to talk about what that's called, and we're going to graph other ones, but I just want to draw that picture. Also note for the inverse, for the exponential function, the x-axis was the asymptote. We noted that. For the inverse, the y-axis is now a vertical asymptote. So I'm just going to write this under my domain and range, that I have a vertical asymptote of x equal to 0, meaning the y-axis is my vertical asymptote. How do I know that? Well, the clue is that my domain starts at 0, but it's not equal to 0. It's never going to be equal to that. So much like we did when we talked about inverses of functions, the next thing we're going to do, and I'm going to do this with you because this is where the new stuff really begins, we are going to now determine the inverse of 2 to the x analytically. And you can talk me through the steps because you have done inverses. We did them in class. What's step number 1 to find the inverse of this? You substitute a y. The first step is strictly notational. Instead of having f of x, I'm going to write this as y is equal to 2 to the x power. What's step 2? Step 2 is actually finding the inverse. We flip-flop the x and the y. So I get x is equal to 2 to the y. This is the inverse. Congratulations. Now, step 3. In my ordinary functions, we've done this. Step 3 is to do what? Oh, now here's where I've got a problem. Okay, because now what I'm supposed to do next, step 3, is I'm supposed to solve this for y. But I have no tools in my algebra tool belt to be able to solve this for y, because I don't know how to get that y out of the power. So this is where we have a definition. Okay, this is where we have a definition, and then we'll come back and I'll show you what the inverse function is going to be. But now we've got the definition. We've got the definition of this thing called a logarithm. Now this logarithm is going to look funky. You may or may not have seen it. If you've just had intermediate algebra in high school, you've not probably seen this. All this is a definition to resolve this problem. Okay? I can't solve this for y. I really, really, really want, as a math person, a way to write this as y equals something. And so to resolve that problem, we make up a definition. It says for all positive numbers a, meaning my base, where a is not equal to 1, the following two things are equivalent. X equal to a to the y, which is the format of what I just have above with my base is 2. We'll come back to that. Is equivalent to, meaning it's the exact same thing, The mathematical symbol for that is an equal sign with arrows on the ends. That means equivalent to, if you've never seen that before. Y equals log. Log is the abbreviation for logarithm. Base A, so I have a subscript there, of x. Now that's new and different. So what we're going to do when we get to the next page is we're just going to do some practicing with that new definition and get used to doing that. But here's what I want you to note. In my exponential equation, the base, I call A the base. The A over here is called the base. It's the same term for both. And then notice my logarithm is always equal to my power. Okay? So the logarithm is always equal to the power. This is how I remember it. Okay? I know what the base is. I can locate that easily. I know what the power is. I can locate that easily. That helps me in my conversion between these two things. Now, just going back up, we'll finish off finding the inverse. So now that the problem is resolved notationally, what I've got here is x is equal to 2 to the y. So according to my definition, the way I can rewrite this now is that y is equal to log base 2. Now that's a subscript. That's not multiplication. Log base 2 of x. And that is my inverse. When we come back on our next class, we will look at the logarithmic functions and we'll talk about how do I graph them without converting into exponentials and things like that. But today, the big job for us is we've got a new definition. It's funky, it's different. I want to learn how to use it. So here goes. I'm flipping to the next page. Is everyone caught up with me notes-wise? All right, good deal. So in example 2, all we're going to do, I'm going to do one example. I've got 2 for you. We are taking a statement that is true. You see in example 2, 5 to the third is 125. I don't think any of us would disagree with that. And all we're going to do is convert this to a logarithmic statement. We're practicing the definition. That is it. So here goes. Log. What's the base of my logarithm? 5. The base of the logarithm is the same as the base of the exponential. It's 5, so I got a little subscript there. Now this is where I tend to get confused, so I'm going to just write an equal sign here. And I've told you, the logarithm is equal to the power. So what am I going to put on the right side of the equal sign? A 3. So this is log base 5 of 125. That's the odd thing out there. I know what the base is. I know what the power is. So the 125 has to go there. Log base 5 of 125 is equal to 3. So the challenge is, and this takes time, takes using it, is being able to look at this and then see, oh, that's the same thing as base 5 to the third power is 125. You'll get there. It just takes time to do it. What I would like you to do now is exercise 3. 2 to the 6th equals 64 is a true statement. Write that as a logarithm. All right, so I've got my logarithm. What's the base of the logarithm? 2. And then the logarithm is going to be equal to what? The power, which is 6. The logarithm is always equal to a power. So that means the only other number I have to deal with is 64. That's what I'm taking the logarithm of. Log base 2 of 64 is 6. Basically, all this is saying is 2 to what power gives you 64? Well, that's 6. All right, the last one of these I've just put in terms of variables just to see are we doing okay. So convert exercise 4 into a logarithmic statement. So I've got the logarithm. What is the base of this logarithm? M. The base of the logarithm is the same as the base of the exponential statement. The log base M of something is equal to what? N, the power. And so then the only thing that's left is this t. Log base M of t, t is what I'm taking the logarithm of, is equal to n. Fantastic. All we're doing is practicing the definition. Question, comment, concern. My next example, we're just doing the reverse. So now I'm giving you a logarithmic statement, and we're just practicing the definition again. So I've got log base 6 of 36 is 2. Trust me, that's a true statement. So if I'm converting it to an exponential, what is the base? 6. The base of the logarithm is the same as the base of the exponential. What's the power? And so 6 to the second, I mean, you know that numerically, but the only other thing is 36. So please do that for exercise 5 and exercise 6. Write down those two things in exponential form. So exercise 5, what is the base of that logarithm? 7. What's the power? 0 equals the other number, 1. Great. The last one, exercise 6, what's the base? B, I used B for base. That's clever. What's the exponent? T, and then the only other thing is the letter R. Again, we're just practicing. And we're going to continue practicing in example 4. Now we're going to use this definition to solve equations. Okay, so I've got x is equal to log base 8 of 4. The logarithm is a new function. I do not know how to solve it in that form, so what I'm going to do is I'm going to convert it to exponential form, something I'm familiar with. So let's do that. What's the base of this statement? 8. What's the power? Logarithm is always equal to a power, so x, and 8 to the x is equal to 4. Fantastic. We just did this a little while ago at the end of the previous section. We can solve that now by equating the bases. 8 and 4 are both based on what value of a base? 2. Lovely. So 8 is 2 to the 3rd power. 4 is 2 to the 2nd power. On the left side, I have 2 to the 3x. On the right, I have 2 to the 2. That exponential equation can only be true if the powers are equal. So 3x equals 2. So my value of x is 2/3. And there's my solution. So please do the same thing with the one below it. Okay, we're moving down 1, and then we'll go up to exercise 8. Do exercise 7. Log base x of 16 is equal to 4. First step, let's write this as an exponential. So what is the base? X. What's the power? 4. Logarithm is always equal to the power, and that's 16. So then what value, when I raise it to the 4th power, gives me 16? 2. Now you might be thinking, hey, Kirkster, -2. -2 raised to the 4th power gives me 16. And you'd be totally right, but here's the thing. When we started considering exponentials and now logarithms, if you think back to when we talked about exponentials, we have only been dealing with bases that have been positive. Because when you have a negative base on your exponential, it is a super cool function, but that's not for our dealing. You might talk about that in calculus or some discrete mathematics someday if you want to be a math major. It's so much fun. So just going back to this definition, on the first page, when you are solving these problems, your base is always a positive number. That's why I don't care about the value -2 to the 4th power being equal to 16, because we are only considering values of the base, values of A, that are positive numbers. So the solution set here is 2. Now remember, that's only applying to my base. That's not saying that my power can't be negative or anything else. It's just my base. All right, exercise 8. Same sort of thing. So now my base of this logarithm is going to be 4. My exponent is 3/2, and that's equal to x. So there's not much to do to solve this other than evaluate 4 to the 3/2 power. When we talked about exponents and fractions, the 2 down here, what does that tell me to do? We're taking a square root. Okay, it becomes the index of my root. So this becomes the square root of 4 to the 3rd power. We talked about that back in the last unit. The square root of 4 is 2, and 2 to the 3rd is equal to 8. So that is my solution based on doing the arithmetic. Questions, comments, concerns? All right, one more of these. Exercise 9. All right, the base of this is 2. The exponent, the logarithm, is always equal to the power, so 3. And 2 to the 3rd power is equal to the x plus 1. The x plus 1 is in the parentheses. That's what I'm taking the logarithm of. So 2 to the 3rd, that's 8. I'm going to subtract the 1 over. and I get that my value for my solution is 7. So that's just been a bunch of problems that has allowed us to practice the definition, and there will be in the homework more problems to practice the definition. All right, we're going to get to a place where we can just have a nice resting place for the day and for this week. So just a few more things. We've got about 10 minutes to go. The first thing here, common logarithm. This is just some terminology that you're going to see as you go through. You will use logarithms in, depending on where you go in some science, some biology or physics or maybe economics, things like that, classes. So there's 2 logarithms that are used more frequently than any other. The common logarithm, that is a log with a base of 10. That's called the common logarithm. It's used a lot because our number system is base 10. So that's why we use the common logarithm. The reason that I mention this is notationally, most calculators, not the calculator on the Apple phone, but most calculators, if they're referring to the common log, will just write log with no base. Kind of like with the square root. We don't tend to write the index of 2 just because it's used so frequently. I don't care if you write log with the base of 10. I'm just putting this here in case you see this and you know that it's referring to a log base 10. You can assume it to be true. The other one that's used more often than not is what's called the natural logarithm. Natural logarithms used a lot because in natural settings, growth and decay tends to happen with the following base. In economics, things grow at this base. The base of this is the irrational number e. We're not going to do a whole lot with e. If you take pre-calculus, you'll see it because it's based on a limit. It's approximately equal to 2.71 and some change. I'm not super concerned if you know that trivia. I'm just trying to give you a little context here. The natural log is the log base e of x. And what you will commonly see on calculators or in writings or wherever you're reading this is instead of using log base e of x, you'll see ln for natural log. So when you see an ln, you can assume that the base is e. When you see an log with no base, you can assume the base is 10. I just wanted to mention that so as you're doing problems. So here's what we're going to do with the time that we have. We're just going to, for a few minutes at the top of the next page, we're just going to talk a little bit about some trivia regarding logarithms. And then when we come back next time, we will apply it. Okay, so that this will be how we end. So just a few things about logarithms, these properties. We could call this logarithm trivia. You can impress your friends and family members over the weekend at parties with all of this trivia. So here we go. If you're taking the log, no matter what the base is of 1. Now we could solve this if we wanted to be super clever. If I wanted to know, okay, log base a of 1 is equal to what? I don't know. Well, let's make this an exponential statement. The base of this is a. The power is the question mark is equal to 1. Well, what power in place of the question mark will always give me a value of 1? 0. All I'm trying to do here is if you blank on these powers on the homework or on the test, you already have the capacity to figure it out. Okay, so log base a, no matter what the base is, if you're taking the logarithm of 1, that always gives you the value of 0, because any base to the 0 power is equal to 1. These next 2 properties right here, these next 2 properties are because the logarithm and the exponential are inverses. That's what precipitated this whole section, was the fact that they're inverses. So what I have here is I've substituted an exponential into a logarithm. Notice that the bases are the same. As long as the bases are the same, they cancel each other out, and I just am left with the value k. If the bases are different, you can't say that. We'll learn how to deal with that situation when we come back next time. Same thing for this next one. In my exponent, I have a logarithm. Again, the bases are the same. That is the key bit of information here. So as long as the bases are the same, if I have an exponential and in that exponent I have a logarithm, then again, they cancel each other out and the value is k. So these last three properties are based on the fact that our logarithm is a power. And so I'm just going to tell you what the properties are. You don't need to know to do anything with them. We are going to practice them when we come back. We'll use these properties to be able to solve equations. That's kind of the point that we're leading up to here. So the first thing is the product rule. The product rule. If I have log base a of a product, meaning of, let's just say, x times y. Well, let's think about our powers. What do we do with our powers when we multiply? Is the example I did earlier. When I multiply my bases, what do I do with my powers? I add them. I add the powers. So if I'm multiplying right here, the way that I can rewrite this is I can say, okay, that means I have the log base a of the first thing, the x, plus, because I'm adding the powers, the log base a of y. That's called the product rule. It's called the product rule because in the parentheses here, I am multiplying the two things. That's why I call it the product rule, x times y. And what I do is I can add each thing individually. The quotient rule, if I have log base a of x divided by y. Well, again, remind me, when I divide, what do I do with my exponents when I divide? You subtract. Okay, same thing here. What am I going to do with my powers, my logarithms? I am going to subtract them. Log base a of x, that's the numerator, minus the log base a of y. Finally, what's called the power rule. So if I have the log base a of, let's say, x to the n power. So I've got a power to a power. I've got my logarithm to a power. What do you do with exponents when you have a power to a power? What do you do with the powers? You multiply them. So what we're going to do here is we're going to take this n, and we're just going to bring it out to the front, and we're going to have n times the log base a of x. I take the power, and I put it out in front and multiply it times the logarithm, which is a power. Before I let you go, I just want to show you one of the cardinal sins of logarithms. It's kind of the same thing as one of the significant errors for exponents. If I have the logarithm base a of x plus y, students every semester want to do this. You want to generalize. I cannot do anything with this. This is not equal to, it is 100% wrong to do this. To say, oh, I'm going to go ahead and distribute log base a of x plus log base a of y. Pardon me. That is wrong. Don't do that. We're not distributing anything. These properties are based on the rules of exponents. All right, so that is where I'm going to leave you today. Yes, sir.